So, we have been saying in this course that there are two kinds of problems that we want to solve. One is the configuration problem and one is the planning problem. And the difference between the two is that in the configuration problem you are looking for a node which satisfies certain criteria and you are happy if you have found that node. But in a planning problem you are in a given situation and you want to be in a goal situation and you want to know the path from the given situation to the goal situation or from the start node to the goal node. Now, in the last 20 odd years or 25 years, the planning community has kind of emerged out of general search and devised their own machinery for doing planning. The idea is to do planning like the idea was to do search in a domain independent fashion. So, it is not that we are planning for a particular problem, but we are writing planners which will work in many problems. So, the same idea carries forward, it is just that the mechanism is a little bit different and we will look at that now. So, the first thing we will see is that we are looking at an action view of problem solving. So far, our view of problem solving using search has been state centered. The state space is the arena for search. The solution is expressed as a sequence of states. The path is expressed as a sequence of states. Even when we talk of the solution space, the solution, for example, for the TSV problem is expressed in terms of states essentially. The planning community takes an action-centric view of problem solving. So, we talk about actions, we give names to actions and talk about these are the actions that we want to do. So, even when we are using the phrase state space planning, solutions are expressed as sequence of actions. Actions are applicable to states, we will see what this is mean, or sometimes relevant to goal description. So, we will design or we will describe a set of operators or actions and we will see under what conditions are they applicable to a given state and also under what conditions is an action relevant to achieving a goal. This will give us ability to even do what is called as goal directed planning. Then we will look at plan space planning which represents only actions, it does not represent states at all and that will come a little bit later. But first we will look at state space planning, but we will look at the machinery of planning. Now, there is a book by Gallup now and Traverso called Automated Planning Theory and Practice and subsequently they have actually also written a newer book, but essentially in that book they say that planning is the reasoning side of acting, that any agent has to act in the real world, but before acting the agent has to do some reasoning. So, what we call as deliberation. Remember we said that an agent has a 3-stage process: sense, deliberate, act. So, we are talking about a deliberation part essentially. So, an autonomous agent in some domain may have certain goals to achieve, may have access to a repository of actions or operators, may use search or other methods to find a plan and executes the plan and monitors it as well essentially. The goal driven behavior of an agent is to perceive or sense its environment, deliberate, find a plan to achieve goals and act, execute the planned actions. So, we have seen this diagram earlier and this is what we will talk about in a little bit more detail. So, a planning agent can perceive the world and produce actions designed to achieve its objectives. So, you are assuming that the planning agent has some objectives, it can see what is happening in the world and then produce the actions that are required to achieve its objectives. So, in a static domain the agent is the only one who acts and so far we have been looking at static domains only except when we looked at games. A dynamic domain can be modeled by including other agencies that can change the world. So, let us look at each of these in a little bit more detail. Let us talk about perception. Domains can be modeled with various degrees of expressivity. In the simplest domains, the agent can perceive the world perfectly. The agent knows exactly what is happening in the world. That is true even for the board games that we spoke about. These are called complete information domains, but in the realistic situations, the agent may have only partial information. We never have full information of what is happening in the world that we are operating in. The objectives of a planner, the goals or objectives of an agent can be of different kinds. The simplest kind of goals are called satisfaction goals on the end state, that we want to be in a final state which satisfies certain properties that we have described. So, we can give a goal description and the end state must have those properties, and they have to be achieved for the plan to be a valid plan. But we can also talk about soft constraints on the end state, that we may say, okay, I would like to do this to be true, I would like this to be true, and so on and so forth, but may not all be achieved. So, for example, typically when we go shopping, we have certain goals that I want to do this, I want to buy this, I want to buy this, maybe I want to go and eat in a restaurant and then come back, but you may not achieve all of them. Maybe you forgot to buy a toothpaste or something, but that is fine, at least you have achieved some of your goals essentially. And under those conditions, we talk about soft constraints, which means that if you do not achieve some of the goals, you may have to pay a penalty. The plan may be penalized in terms of how good it is. Then we can talk about trajectory constraints. So, trajectory constraints are constraints on the path that the planner finds, and it is not just on the final state essentially. So, for example, if you are driving around the countryside, you may want to say that at all points find me a route on which on all points I am not more than let us say 50 kilometers away from a medical center or from a restaurant or from a petrol pump, whatever the case may be, but the trajectory has to satisfy certain constraints as well. So, those kind of constraints are called trajectory constraints. Then we can have soft trajectory constraints, that we have trajectory constraints, but they are only desirable, they are not necessarily hard constraints. As long as you can do that, then we are happy with the plan. Then we talk about actions. What are the kind of actions that agent can do? So, actions may be deterministic, always achieve the intended results, and we have been talking about deterministic actions. If you say pick up a block, then you end up holding it, or they may be stochastic, we may or may not achieve the intended results essentially. So, for example, just imagine if you are walking on some slippery ice or snow and you may want to take a few steps forward, but you may find that you have slipped and fallen on the side or something like that. So, those are stochastic actions, and there is a whole community which looks at stochastic actions. They look at this process called MDP or Markov decision process planners, in which the stochasticity is built into the modeling of the domain. Then actions can be instantaneous, which means that we do not have a notion of time. If we say pick up something, that means it is done in an instant. So, we do not even represent time in the simpler domains, and we assume that the actions can be done instantaneously. But in the real world, of course, actions can be durative, which means they have a duration. They have a starting time and an ending time essentially. So, if you are, for example, boiling water for making a cup of tea, that takes a certain amount of time, and planning with durative actions is, as you can imagine, harder than planning with instantaneous actions. We will stick to instantaneous actions in our course here. Actions may have an associated cost essentially. We have seen that when we started search, we did not associate cost with edges, but now we can add cost to edges, which means that plans can be evaluated based on what is the overall cost that the plan incurs essentially.
So, one doubt.
Yeah.
If we say an action is deterministic, it cannot be instantaneous or durative. Is that so?
No. Actually, these are different dimensions. So, there are two different dimensions. One is that they are deterministic or stochastic. Again, if I give you the example of walking on snow or ice, it can be thought of as a durative action essentially. But if you talk about some domain where there may be actions which are instantaneous, but also stochastic essentially, as to which square to move to next or something like that. So, these are different dimensions, deterministic versus stochastic and instantaneous versus durative essentially, and there can be any combination of those. Then we have already said that we assume that agent is the only one who is acting, making changes in the world, and that actually makes planning itself a hard problem. It has been shown that even in the simplest of domains, planning is in p space, which means it takes polynomial space and exponential time. There may be extraneous events which are happening. For example, rain may be happening, or if you are living in a city, then shops may have opening times and closing times. So, your plan has to conform to those constraints that you have from extraneous events essentially. Then of course, there are multi-agent systems. We have already spoken about games and game theory. So, there may be collaborating agents, or there may be adversarial agents, or there may be agents which may be competing for common resources essentially. So, for example, it happens in real world that people compete for the same jobs or admission to a university, as the case may be. They are neither collaborating nor are they adversarial, but they are competing for the same resources. So, in a way they are adversarial essentially. Now, the simplest domains are called strips domains, and this is an acronym for Stanford Research Institute Planning System. Some of the first planners were developed in Stanford Research Institute, SRI it used to be called at one point. They involve finite, static, completely observable environments essentially. The set of states and the actions is finite. Changes occur only in response to actions of agents. The agent has complete information of the state, and there are no other agents essentially. So, on all the dimensions that we saw, these are the simplest that can happen essentially. The goals are hard constraints, and they are on the final state only, and the goals have to be achieved for a plan to be valid, because we have said that they are hard constraints essentially. Then actions we assume are instantaneous. There is no explicit notion of time essentially. We just say this action happens and this action happens. There can be sequencing, but there is no notion of time. You can't say that while I am boiling water, I will chop the vegetables or something like that at the same time. So, because these are durative actions, and then time has to come into play. Then actions are deterministic. There are no accidents when you do something. There are no execution errors or stochastic effects. Whatever action is intended to do, that thing happens. So, if a robot is moving 5 steps in one direction, then it ends up at 5 steps in one direction. So, such planning systems can be modeled as state transition systems essentially. So, and we have been looking at state transition systems in a way when we looked at state space search. So, the simplest domains can be modeled as state transition system, which is defined as a triple which contains a set of states, a set of actions, and a function which will map states to actions. So, S is a finite set of states, A is a finite set of actions that the actor may perform, and gamma is a function which takes a state and an action and results in a new state. So, this is a state transition function, that how do you go from one state to another. It's if you do this action A, then you will go to some state. If you do an action B, you will go to another state, and the state transition function tells us that essentially. If an action A, we will use lowercase letters A, B, C for actions. If an action A is applicable, and we will define what we mean by applicable in a short while. So, if an action A is applicable in a state, then gamma S of A is a resulting state. So, this also stands for the resulting state, and that is a function from S cross A. S is a set of states and A is a set of actions to a new state essentially. So, this gamma S y stands for that as well. Now, over a period of time since the mid 90s, there has been a sequence of series of languages that have evolved. These are called planning domain description languages. So, the idea here that unlike when we did in search, we said that we did not pay too much attention to representation. We said we assume that the user will give us a move gen function essentially. But in the planning community, they say no, we will tell you how to describe the state and how to describe actions. So, we will look at some of them for the simplest domains. So, in modern times, as I said, a series of languages with increasing expressivity has been defined to bring uniformity to planning research essentially. What do you mean by increasing expressivity? That you can include, for example, durative actions and other kinds of constraints that we talked about. For each such domain type, a language has been defined essentially. The idea is that researchers working on planning problems can use these standardized representation. So much so that if you look at the planning conferences, they often have planning competitions in which they have specified the PDDL that they are going to be using, and participants have to write planners using that PDDL, and then they are given test problems and tested as to which one finds a plan, which one finds the shortest plan, or which one plans the in so much time. All these kind of competitions are happening, and that's possible because the representation has become standardized. So, components of a planning task as expressed in PDDL, the things in the world that interests us, these are the objects essentially. So, for example, there is a block called A and a block called B, and whatever is the domain you are talking about, there is a set of objects in the domain. They are properties of objects that we are interested in essentially. So, for example, block A is on the table and things like that. There is an initial state description, the state of the world that we start in essentially. And that is, of course, we have been looking at this kind of an approach all this while, that there is a start state that is given to you. And there is a goal specification, things that we want to be true essentially. So, goal is not necessarily always a state, it can only be a part of a state description, and so we will call it as a goal specification. So, we are only concerned with that this predicates must be true in the final state, and then we are happy. We do not say that this should be the complete final state. So, a goal specification or a goal description can apply to many states essentially. For example, if you simply want to say that block A must be on top of block B, and that is all you care about, and the rest of the world can be whatever. And then we have actions or operators, ways of changing the state of the world. So, sometimes we discriminate or distinguish between operators and actions. Operators are generic in nature. So, you state things like pick up block X essentially, whereas actions could be grounded or they may be specific, which says pick up block A, for example. So, actions are basically instances of operators. So, I said that there is a whole family of PDDL languages that have been evolved. Let us look at the names of a few of them. The earliest language was PDDL 1.0, essentially the strips domain essentially. What is the strips domain? If you remember, actions are instantaneous, agent is the only one that is acting, actions are deterministic, the world is completely known, and that kind of stuff. Then there was a language in which we added conditional effects. So, what is a conditional effect? That effect is true. So, every action, as we will see, has preconditions and has effects essentially. So, if the preconditions are true, then the action will be applicable, and if the action is executed, then the effects or post conditions will become true. But sometimes those post conditions can themselves be conditional in nature. So, an example of that is that if I put a book in my bag and then I walk to my office, then is it true that the book is in my office? So, the condition for the book being in the office would be that the condition that it is in the bag. If I do not put the book in the bag and I walk to the office with an empty bag, then the book will no longer be in the office essentially. So, the conditional effect says that if, for example, the book is in my bag and if I walk to the office, then the book will also be in the office essentially. So, this is a little bit more complex and simple actions which do not have this kind of additional conditions. Then we talk about numerical fluents. So, fluent is a word we use for predicates which can change in their value. So, for example, you can measure how much petrol you have in your motorcycle or something like that, and that could be a part of your planning exercise, that you want to travel from across the country or something, then you have to keep track of how much fuel is left and when do you need to fill in your tank again. So, numerical fluents will take care of that. Then we can have plan metrics as to how do we measure the cost of a plan. Then as I had said earlier, you can have durative actions. So, all this is possible in PDDL 2.1 essentially. Then in the next language, we have something called derived predicates, which are the consequences of effects. So, it's like saying that if some effect is true, some predicate is true, what else is true as a consequence of that? That whatever else is true as a consequence of that is not described as part of the operator or the action, but it is described as a derived predicate. So, if this predicate happens to be true, then something else will also be true essentially. So, for example, if you are living in a warm city like Chennai and suddenly you were to bring a large block of ice and keep it in a room, then in a way the consequence of that, this thing will, the room temperature will come down essentially. So, that is not described as part of the action of bringing a large block of ice into the room, but it is a derived effect, because if there is a large block of ice in the room is true, then of course, the room will become cooler or something like that essentially. So, these are not part of actions, but if the effect becomes true, then certain other things also become true. That is in PDDL 2.2. Then there is something called timed initial literals to model exogenous events, that it allows you to say that certain predicates become true at certain times, and you can specify that. The shop opens at 9 in the morning or 11 in the morning, depending on which city you live in, and closes at this time. So, these would be modeled using time initial literals. So, you can see that we are modeling exogenous events also at this point. Then we said that richer languages will have things like trajectory constraints. So, how do you specify constraints on the trajectory, that the path must specify this kind of property. So, these kind of constraints may be, for example, that let us say you are having a cooking plan, and then you might say that every time you open the refrigerator door, it must be followed by closing the refrigerator door. So, that is a constraint on the trajectory, that you can't open the refrigerator door. Of course, some people might, but you can't open the refrigerator door, forget about it and go and finish your cooking and then go off or something like that. The trajectory constraint says these kind of things, that if you open the refrigerator door, then in the plan there must be also an action for closing the refrigerator door. It does not have a end effect on the final condition. Your dish that you are preparing may be ready. The fact that you left the refrigerator door open does not affect that, the condition on the end state, that is the goal of your plan, but it is a constraint on the trajectory, that you can't leave it open. Then you can have soft constraints, which are also trajectory constraints, which can also be trajectory constraints. Then in PDDL 3.1, we can have object fluents, we can have functions that could return objects essentially. So, that could be part of this thing. Some objects become true at certain point and so on and so forth, or they can be computed using a function. So, as I said earlier, we will confine ourselves to the strips domain, which is the simplest possible domain. We will relax this a little bit towards the end, when we will say that what if there are two agents trying to solve a problem. But that can also be modeled as, let's say, you are talking about a robot with two arms. So you can think of each arm acting independently.